Hey everyone, today we have an immense pleasure to have James Douma with us. This is the two-part series. The first part will explore how self-driving works in general, and also how do we train self-driving, basically the building blocks of self-driving. And in part two, we will look at what the vehicle is thinking. So as the vehicle drives down the road, how does it process the information? How does it make decisions? So this is a two-part series. It's going to be quite a while, so it's good if you have some time, sit down and really digest the information that James is sharing with us. I think it's really good content that's coming out, so find some spare time, sit down and listen to it. Also, if you like the content that's coming on this channel, please remember to like and subscribe. Also, big thanks to James, Deborah and Dave for making all of this happen. Perhaps how does self-driving work? I understand like the vehicle kind of have to have first they have to have their own perception. They need to be perceived the environment, and then they need to be localized. So for Tesla, like how do they do how do they do it?
So Tesla is doing it a little bit different than most of the rest of the industry is. It's kind of hard to talk about Tesla sometimes without talking about how everybody else is doing it, because a lot of the sort of public dialogue is rooted in this perception of how like self-driving works. Tesla is doing an approach where they're kind of building the car with the same kind of system that an animal has. Like they're not starting from a place where, for instance, it has maps that have a detailed understanding of the environment, right? So much like, you as a person, when you're first seeing something, or an animal when it comes into a new situation, you use your senses, you look around the environment, and all of your understanding of the situation is based on your understanding of the rules of how things are supposed to work and what you see right now. So Tesla's perception system, it's basically just cameras. I mean, there's other stuff. They have an IMU, and of course they have GPS, but they lean very heavily on cameras and visual perception of the environment. And this is what people do when people drive. And people are overwhelmingly visual. I can take away your sense of smell and your hearing, and you can still drive a car. But if I take away your vision, done. You can't do anything at all, right? It's totally based on vision. Yeah. And so Tesla's car system is similar to that. They're just using vision. So vision is the sensors. Vision looks, the car has 8 cameras, 8 outward-facing cameras that look at the environment around it and essentially pull in a bunch of images. Then the system in the car assembles those images into an understanding of the situation that it's in. What's the environment? Where am I? What's moving relative to me? What's the road like? Am I at an intersection? Like, what rules apply to me at this point? It develops that understanding, right? Then there's, so that's what we call perception. Perception. So sensing is what the cameras do. They generate the images. Perception is the process of taking the senses and converting them into an understanding of the situation that you can act on. Then there's planning, which is you take the understanding of the situation and you take a goal that you have. The user has given you a goal, like I want to go to this place, right? And you have these other goals built in, like you want to do it safely, you want to do it quickly, right? Yeah. And so given those constraints, what the planning system does is it takes the current situation, and then it says, okay, so in order to get to the goal, this is the next thing we need to do, or these are the next few things we got to do. So that's what perception is. Then action is a thing that happens after you have a plan. So once again, you got sensing, what the cameras do. You have perception, which is the system that sort of tries to understand what the current situation is. Planning takes that understanding and a goal and turns that into a plan for what we need to do next. And then there's action, which is the part of the car that actually does it, the part that turns the steering wheel, presses the brakes, and that kind of stuff. So you sort of have these, I guess, I usually think of it as 3 stages, but you could think of it as 4 if you want to separate the cameras from perception. Okay, so in Tesla's case, they do perception almost entirely with a neural network at this point. Now, so the history of Tesla's system, Tesla's been working on self-driving systems for quite a while now, since about 2014. Internally, they had an AP1 car that they released in 2015, which was based on a Mobileye kind of off-the-shelf ADAS system that Tesla added their own stuff to. And then toward the end of 2016, they came out with their own built from scratch system, which is basically a system that we have in the cars today with all the camera. The system today, the car itself has all the actuators so that it can drive itself. So the computer can take control of the brakes, can take control of the steering. It can do all that stuff. There's a computer, of course, inside the car that makes all these decisions. And then there's a set of sensors where it senses the environment. So that's sort of the set of hardware. The one thing that has changed in the hardware over time is the sensors, the cameras, are designed to be modular so they can be replaced in the cars. And the computer is also designed to be replaceable. And of course, one thing that happens as time progresses is that the amount of computer that you can get for a certain amount of money, it goes up and up and up. So because it's taken longer than ideally they would have liked to get to market, the opportunity to put a faster computer in the car comes around and they replace that. So the car currently has what's so-called hardware 3 in it. So strictly speaking, these hardware designations, like hardware 1 was the original Mobileye system. Hardware 2 was the first version of the system that has all the cameras and whatnot. There was this intermediate hardware 2.5 that had upgraded cameras, slightly different cameras, but it kept the old computer, the GPU-based computer that the original car had. And then in late 2018, they came out with hardware 3, which was basically changing out the computer too. And the hardware 3 computer has Tesla's custom FSD chip in it.
Sure.
Okay, Tesla's custom chip is designed to run neural networks really, really fast. It's highly optimized for running neural networks. Now, the software progression has been, it started out with very simple neural networks on the cameras, like back in, say, early 2016 on the individual cameras. And at that time, the GPUs in the car were basically, they're running, compared to the neural networks that are running today, they were very simple neural networks back then. They took much less compute power. They had many fewer layers. They were trained on a lot less data. And the number of different sort of things they would tell you about your situation was much smaller than it is now. And then there was what I'm going to call heuristic code, conventional handwritten, human-written code that would take those perceptions, and it would do all the planning. Some of the perception was done in handwritten code at that time also. All of the planning was done in conventional heuristic. And of course, the action stuff was all done in that code. Now, over time, as the system has been developed, the neural network portion has gotten bigger and more complicated. And now the total amount of functionality the system does has grown quite dramatically. But even so, the fraction of everything that's done by the neural network itself has grown quite a bit. So there were a lot of sort of basic functions that used to be performed. Like, for instance, in the beginning, the cameras were all separate, and each camera would say in its field of view, what does it see? Its outputs would be, this is a car, this is a stop sign, this is where you can drive, right? This is a wall, these are pedestrians, and it would be all in the field, the point of view of the camera, right? So at that point, the heuristic code behind that was basically taking all of these different views, and it had rules where it would try to synthesize an understanding of the system based on these perceptions. For instance, if you have a camera ahead of the car on the passenger side, there are at least 3 cameras that can see that, right? And so your system has to know it's not 3 different cars. They're all the same car. So that code, it has to sort of understand the fields of view of the different cameras, make a guess about where that car is in space, and then correlate that with the different cameras, right? This is one of the reasons why there's 3 cameras in front of the car. And there's the B-pillar camera looks kind of forward and kind of to the right. The B-pillar camera is the camera that's, the B-pillar is the structure between the front door and the back door on each side of the car. And so just to recap, Tesla's cars have 3 cameras in a module that sits in the front that look forward. They have a narrow field of view one that looks way down the road. They have a kind of conventional field of view one that more or less sees, what you comfortably see out the front windscreen. And then they have a pretty wide angle field of view camera also. They have 2 B-pillar cameras that look to the side and forward, so kind of out that way.
Sure.
They have two cameras in the repeaters. Now, the repeater is a repeater on a car. It's a little widget that sits on the front fender that frequently has a turn signal indicator in it. And in Tesla's case, it has a turn signal indicator and also has a little camera mounted in it that looks backward and to the side.
Oh, okay.
And then they have one car that's just above the license plate that looks straight back from the car. So that's the full set of cameras that they've got. So all of the cameras have overlapping fields of view. And strictly speaking, there isn't any position you can be around the car where at least two cameras can't see you. So the car has a certain ability to triangulate. Okay, so in the beginning, they had a neural network that was on each one of these cameras that just basically would say, I see a pedestrian at this point in the frame,
sure,
and I see a fire hydrant at this point in the frame, and so on. And then some handwritten code, some code that was written by a human being, would have to take all those different perceptions from the individual cameras and synthesize it into kind of an understanding of the whole situation. There's a car here, a pedestrian there, I'm on this kind of road, I'm in the right lane, and so forth, right? So over time, as the system, as Tesla has incrementally modified the system to make it more sophisticated, and an integral component of that has been that the neural networks get bigger and bigger and bigger. So the neural networks in the full self-driving, by comparison, like there was a fairly simple neural network that just looked at each camera, and for each frame that came in, it would just label a bunch of things. And so originally the computer would just get this stream of updates in the fields of view.
Sure.
Now, it's after many versions and a number of years, they now have a system where they have the outputs of those neural networks feed into another neural network that synthesizes all of them into a singular view and puts it in a top-down frame. So this is the bird's eye view frame. So instead of trying to understand the environment from the perspective of the car, it sort of has this God's eye view, this looking down on the car from above. That's the way they bring all the cameras together, is they put it in that framework. Okay. And then they put that into a grid so that it also has some height, like they guess at the height of things that are in. Then they integrate that across time. They don't look, originally, all of the decisions were at this instant in time. And to the extent that the car had any memory, it was the human written code remembering what it was doing or what it saw, 2 seconds ago or 5 seconds ago. And so to the extent that you needed to remember the last few seconds or the last few minutes or the last few hundred feet, that code did that. Now it's very different. The current system has a memory both in space and time. So, and this also exists inside the neural network. The neural network remembers not just what it decided before, but it remembers all the details of what it thought about the situation before, so that at each moment in time, it refines and builds on that understanding of what's going on. So what that does is that makes what the neural network is seeing right now more accurate, because it's not every instant is a standalone instant anymore. It's that every instant relies on the last few seconds that it saw and the last, say, 50 meters of travel distance that it saw. So basically, the neural network now brings all the cameras together, synthesizes them into an overall view, and then synthesizes that across space and time to produce an even better understanding. And just recently, in the latest version, they've started going a little beyond that. Up until very recently, the output from the neural network was kind of this map. And it would be a map of the space around the car, and it would be like grid paper, so like all these little boxes on a Cartesian grid, and in each box there would be labels for what was in that box. So for instance, if you had a pedestrian in front of the car, the pedestrian would occupy, you could imagine each box is about 1 cubic foot. It's about, say, 30 centimeters by 30 centimeters by 30 centimeters, right? And inside each one of those boxes, the neural network would say what was in that box. And it might be nothing, because it might just be empty space, or it might be that a stack of boxes would be a pedestrian. If you have a pedestrian that's 2 meters tall, then, you've got, 6 or 8 of these boxes. And then the pedestrian might occupy multiple boxes horizontally. You might have multiple pedestrians. So you would have them, the edges of the road, the boxes for those, they would have road edge, road edge, road edge. The ones for the road surface would say road surface. Trees would have trees, walls would be walls, and so on, right? So the output from the neural network would be like this volumetric map. It would be like LiDAR on steroids, where you had this sort of volumetric map, except everything was labeled inside it. Not just there's something here, but what's there? Like, is it a dog? Is it a bicycle? Is it a sign? What's on the sign if it is a sign, and so on. All that stuff would be in the map. So then the code that digested that would basically look at this map, and then that code would then decide. Now this is human being created code. So recently they just started taking this step of having the deciding where everything is be done also by a neural network. So this is another layer of neural network that's going on. So the output of this neural network isn't, here's a bunch of boxes, and these boxes are all labeled car, and there's a bunch of them, and these are labeled truck, and these are labeled road. Instead, the output is there's a road, and you're on it. And there's a car, and it's there, and it's going that fast. So instead of having a whole bunch of boxes that the software looks at to figure out what kind of car it is and where it's at and how fast it's moving, instead, the neural network just says, that's a car, it's there, it's going in that direction, it's going this fast.
And all this is done in real time?
Oh, yeah.
Oh, wow.
It's it's kind of super real time from a human being standpoint, because it's 36 times per second for the whole system. So the entire understanding of the system is completely refreshed 36 times a second. So
Okay, so how is this different from right now? They're doing it. They're doing it this way versus the previous time they're using humans like labeling the thing. So how is it? Is the new code way better than the previous version?
So, it's better. It's harder to do, and it's more complicated, and it takes more time to get working, which is why they didn't start with that.
Okay.
Like every time they revise the system, they revise it to have a higher level of functionality.
Sure. And
more accuracy, and to be easier, to take fewer man hours to do it. So, you're probably aware that the process of creating a neural network, right, is a neural network is a web of very simple computational elements, kind of in an abstract sense. These aren't physical elements. They're logically created inside the software. And each one of these elements, they're called a neuron. So the neural networks, they're loosely modeled on the idea of how the brain works, or at least what people thought the brain worked like, 50 or 60 years ago when the concept of neural networks was invented. But the idea is that instead of having, one big thing that makes these coherent, concrete decisions, instead you have a mass of little things that each learn to do a small part of the job, and they all work together to sort of create higher level stuff. In the same way that each individual neuron in a human brain or an animal's brain isn't very sophisticated by itself. Each one does a relatively simple thing. It has some number of inputs, about 1,000, and it has a small number of outputs, typically one, sometimes a couple. And it makes a relatively simple decision for its output, but somehow that system can learn to do very complicated things. And this is the magic of neural networks, is that you can do a trick where when you train a neural network, a neural network, basically, you give it some input, which can be very complicated. Like a picture is actually really complicated, right? Because it's all of these pixels that have all of these colors. And somehow you have to turn that into, this is a dog, or this is a cat, or a scene at the beach. And that is something that has, it was, for a really long time, it was an example of a thing that was impossible to do. Like, until neural networks, it was not possible to create a piece of software that could tell a dog from a cat in a picture reliably. Like, that had never happened prior to 2012 or something, which is easy to forget today. We have all these amazing neural networks that we use every single day. Your phone can tell you like what kind of bird it is sitting outside your window, right? The security cameras can tell you when there's a human and if they're breaking in or if they're walking away. Like, we can do all these amazing things. You can recognize an individual person from their face or their voice. right? These are all things that weren't possible 10 years ago, right?
Yep.
I mean, basically 10 years ago was the dawn of all this stuff. And the way that neural networks basically do this is you start with with random settings. Your neural network it's a bunch of neurons, and they're interconnected in a way that the creator thinks is amenable to learning the thing he wants it to learn or she wants it to learn. And then you present it with a picture, say, if we're training against pictures. You can do this with sounds or words or something else too, but just talking about pictures. You present it with a picture and say that we want to teach a cat-dog discriminator, a thing that can tell a dog from a cat, right? So I show it a picture and I ask it, is this a cat or a dog? And of course, in the beginning, it's just guessing because it's got no idea. It doesn't know anything. So it says dog. And if it's a dog, you're like, you were right. But if it's wrong, you say, no, that was a cat. What it does is it looks at all the things, every single decision made by every single neuron all the way through the system that contributed to deciding that that was a cat instead of a dog. You ask the question, how should each one of those little knobs have been different in order to produce the dog result instead of the cat result? Now, you don't change the knobs all the way. All of these knobs in these neurons, they go from 0 to 100, say, right? And say you've got a knob that's at 25. And when you look back, the algorithm says, well, if that knob should have been at 50. But you don't go all the way to 50. You just turn it up by 1. You turn it up a little ways. You move it a little in the direction of dog, right? Now, the reason you do this is because if you turn the knob all the way, it'll learn that picture is a dog, but that's the only thing it'll learn. It won't generalize. It'll just know that one picture. But what we want it to do is we want to show lots of pictures of dogs and lots of pictures of cat. And we want it to figure out what makes a dog and a cat a cat. And the way you do that is when it makes a mistake, you correct it a little bit in the right direction. So you do this a bunch of times. And it turns out that for the dog and cat discriminator, if you have like 1,000 pictures, it'll learn to tell dogs from cats really quickly, which is kind of amazing.
Yeah, it is.
You have 500 pictures of dogs and 500 pictures of cat. And this is a thing that, like, if you take a deep learning class these days, or you just do a little online thing, anybody can do this in like 10 minutes. Yeah. It's amazing because it was impossible 10 years ago, right? Like nobody could do this. And now anybody can do it. And of course, with bigger neural networks and more training data, you can train more complicated things. And of course, the field itself is advancing very quickly. Like every year, things happen that the year before nobody thought was going to happen for a really long time. I mean, it's astounding how fast it goes. And of course, Tesla's riding this wave, right? Every year there are new discoveries. And so now there are these new things that they can put in their system to make it even better. And internally, on top of like constantly bringing this new technology into the system, they have a lot of cars collecting a lot of data. So they're constantly getting more training data, and they're building software for doing the training that makes their training better and makes it take less effort. So in the beginning, the way you labeled these images, when it was just those field of view things, and you wanted it to tell you, say, where the road was, a human being for every single picture would have to go to the picture and draw a line around the road and say, here's where the road is. And for every single photo that you wanted to train with, someone would have to label like all the roads and all the stop signs and like, everything that's a tree and a pedestrian. It was very, very labor intensive. Like it would take a long time just to do one image, right? Of course, there's this virtuous cycle that occurs that say, you start training your system to tell, cars from trucks, from people, from motorcycles, right? So in the beginning, you have to hand label everything, and then you train the neural network for a little while, right? And of course, that helps the neural network in the car, but it also makes your tool better, right? Because now you can use the tool. So, you show a picture to the thing, and you've got the human labeler who's sitting there, and first he asks the neural network, well, what do you think, right? And if the neural network's good, it gets most of it right. And so then the labeler's job becomes, well, he just adjusts things. Like, that's not the edge of the car, this is. And the road edge should be here. And that's not a motorcycle, it's a bicycle. You go through and you change these things one by one. Yep. But it takes less time to do that. But this is still in the field of view of the cameras, right? So they worked on that for a while. And Tesla, in the beginning, thought that was going to be enough. And it turned out it wasn't enough. The system needed to do much better than that. And so when they started doing the bev, the view looking down from the top, they went a whole different direction with the labeling, which they call auto labeling now. That's Tesla's internal label for the thing. And auto labeling, instead of taking a bunch of pictures and sort of treating them separately, what auto labeling does, and with these pictures are coming from cars that are out driving around doing stuff. And so what auto labeling does is they have a car drive through an interesting scenario. So I should highlight, Tesla doesn't record all the data from all the cars all the time. Sure. That wouldn't even be useful. It's too much data. You can't use most of it. Okay. Instead, you want examples of the things you're getting wrong right now. So for instance, all of the cars that drive, the software monitors its own performance and it has feedback things. Sometimes some of the internal feedback things are, it uses various sort of signals that something is going wrong. Like it might run two versions of the software, an old one and a new one, and it's trying to get the new one working. And so it'll look for situations where the new one disagrees with the old one. A really notable thing is a lot of times when the human is driving the car, so the system collects data even if people are driving, even if it's not driving the car. So for instance, you're driving through an intersection, right? And the car, the autopilot's running in the background, and it's saying, I think the car should go there, right? Okay. Like, what's the right lane to go into at the next thing? Okay. But the human drives to a different lane. And so the software says, I got that wrong, I'll save it, and then we can use it to train with, right? So instead of trying to capture everything, at any point in time, Tesla is telling the cars, look for this, and if you see it, send it back to me. So once upon a time, it was, we need pictures of green trucks. So if you see a green truck, send me a green truck, because our green truck detection isn't very good. Sure. Later, it was more complicated things like I was trying to predict what the car ahead of me was going to do. And I predicted it would do this, but it did that instead. So then you capture that example. And now when they capture an example, it's what they call a clip, where the car is driving for 20 or 30 seconds. And it captures everything that all the cameras see for that 20 or 30 seconds. And then that goes back to Tesla. It gets uploaded. And it goes into a machine, an auto labeling machine. And what the auto labeler does is the auto labeler tries to guess the 3D structure of the world that those images were taken in. Because when the car drives for 20 or 30 seconds, and you have video from all the cameras, you can run a piece of software because you see a tree go by or a truck go by, right? Or you see the same line on the road for several seconds or whatnot. And because different cameras see it at different times, that auto labeling software, it can look at all that whole clip, and it builds like a 3D model of that whole scene and what happened. And then it labels the model. So for instance, in the clip, you might, if you drive past a pedestrian on the side of the road, he or she, they might be seen in 5 different cameras, and you might have 500 different frames of images of them, right? Now the car knows how fast it's moving and what direction, and you can guess the pedestrian's probably stationary or something like that. So the cameras can know all of these pictures of the same pedestrian, and you see them from different angles and different distances, right? So the first thing you can do is the auto labeler software can be really confident that's really a pedestrian because it saw it many times from many different angles. So the first thing that you get with the auto labeler is the labels are much more accurate just on the first try because it has so much correlated data on every single thing that it sees. The other thing is each one of those, once you label that pedestrian, you can push those labels back to all those individual frames. So if you have 500 pictures of the same pedestrian as you drove past them, once you know it's a pedestrian, the auto labeler does it. One thing that it can do is the auto labeler can label those 500 pictures pedestrian. Pedestrians. Here was the outline, right? So you get that. But the other thing that you get is you have memory over time of what's going on. So a lot of things that you couldn't really tell very well before, because for instance, say you saw the bumper of a car sticking out from behind a wall as you were approaching it, right? Well, when all you can see is the bumper, you're not very confident, right? But once you've driven past it, the auto labeler can go back and say, oh, that was a bumper of a car. So it can label that, even though it was very unconfident the first time. So now the way the human labeler's job is, a clip comes in and it goes into the computer, and the computer generates the 3D scene, and it labels all the 3D objects in the scene, right? So now the human labeler can just look at the scene and say, oh, that's a yield sign, not a stop sign. Or, this is a pothole, not a manhole cover. Or, you go find the 4 or 5 things that it didn't get quite right, and you fix those. And now all of the 2,500 or 5,000 camera frames get labeled, and you get another thing. Because you built that 3-dimensional model of the space that was going through, now you can create the output reference for the bird's eye. So because you've got all this correlated data and a human has looked at it and validated it, now you know exactly what the bird's eye should be telling you about the scene as you drive through it, right? Because you have all that 3D data now. So until they had the auto labeler, they really couldn't do the bird's eye very well, because you really need a 3D output target to be able to train that.
Yep.
So the auto labeler lets them ingest vastly more data, because it used to be they had more data than they could label. Sure. Right. If you had 1 million people, you couldn't label all the data they had before, and so they had to choose what they were working on.
Yeah, and how do they you mentioned that let's say if the label goes in, right, and then they have to find out which one is, maybe it's a yield sign but it's not a stop sign. Does it flag out that there's no confidence on that particular sign, or like?
Yeah,
it does.
So neural networks are inherently probabilistic. So we like, when you use a camera to, I gave the example of like trying to tell what kind of bird it is at your window. You point your Google the bird, right? And Google says, oh, that's an Oriole, right? But internally, what the software had, 100 different birds it could be. And internally, it's like, 60% this bird, 30% that one, 5% this bird, 1%, and so on. So it's everything internal to the neural network is always probabilistic. So when a car is driving down the road and sees a stop sign, it never thinks stop sign. What it thinks is 98.2% stop sign.
Sure.
And then 1% yield sign, 1% tree, or whatever the deal is, right? And so in situations where you have one that you have much higher probability than other things, typically you decide that that's what it is. But you can look at those numbers also to tell how confident you are. Like, say, you see a creature and you get, 58% dog, 49%, or 42% cat or something. Sure. You can say it's probably a dog, but it might be a cat, right? But if it says 98% dog and 2% cat, you're much more confident that it's actually a dog. So internally, that's always what's going on. And in fact, one of the reasons why you want more and more of the system to be neural network over time is because imagine that you're a human you have to write the planning code that says, do I go at the stoplight or do I stop? Right? Sure. Okay, so as a human, you look at that situation and you say, if it says red light, 99%, I'm going to stop no matter how fast I'm going, right? You have to pick a number, 99, 92, 98. One thing that you experience this yourself, right, is that right now the system looks at a situation, and when it sees pedestrians, and it has a probabilistic path it predicts for a pedestrian, right? And if it thinks the pedestrian is going to cross your path, there's a probability. Well, the code that tells the car to stop driving, that's written by a person, and they have to pick a number. So if this is a pedestrian, how low do you set the number before you stop, right? And the thing is, if there's a 0.001% chance that a pedestrian is going to step in front of you, you stop. Sure. Right? You just do, the cyclists and that kind of stuff. So when you were driving, you saw that thing where you were coming to the intersection, there was a cyclist coming and the car stopped. Now, as a human, you could look at that and you could say that was probably an overreaction. But the thing is, the person who wrote the code to tell the car to stop, he has to pick a number, or she has to pick a number to decide. And for that kind of situation, when it's a pedestrian, they pick very, very low numbers, right? So the thing is, it could be that it's very hard for the neural network to be that confident. Like the right number is probably 99.9%. But the human, just in case, they put 99.999%, right?
Okay.
So you experience this as kind of overreacting.
Sure. So how is it different from a human code versus a neural net? So if there's the same situation that happens, right? If it was hand coded versus if it was neural net, like what would the difference be in future as it moves forward?
Yeah. So that decision. So when a human has to write that, do I stop or not? The human has to look at a couple of things coming out of the neural network, like what is the pedestrian probability? And the human might look at a couple of other things, like what is the intersection probability? You know, you might have 2 or 3 numbers. But a neural network, if a neural network was making that decision, it can look at all of the probabilities that come with it, not just the pedestrian, right? For instance, the neural network can look at why do you think it's a pedestrian or not, right? Whereas for a human, it's very hard to write a piece of code where for every decision you make, you're going to consider 100 different things. It's just too hard to do that. But that's inherently how neural networks always do that. They always look at 1,000 things. They always look at, because that's just the way neural networks are built. So the inherently probabilistic, uncertain nature of the output of a neural network is best digested by another neural network that can take into account all of the different little confidences and the whole situation to make a decision. And that's why, as a human being, you can sit in the car and you can see the cyclist coming and you can say, oh, he's going to stop, and it's safe to go. The neural network internally might feel the same thing, but the person who has to write the code to stop, like they can't interrogate every different thing going on inside the neural network. Whereas if you, in the future, that decision will also be made by a neural network. And I mean, Tesla's not doing that yet, but they will. And when they do, the system will get smoother and more accurate. And that's basically the evolution of the system generally. If you drive it, over months and years and you see it change, what you see is that, it gets a new capability, and in the beginning, it's not so great. Like, there was this capability, with the cut-in indicator. This was one that Andrei Karpathy, he talked about, had this feature during the autonomy day, how they developed this. And initially, what they had is they just asked the car to guess if a car in a lane next to you was going to pull in front of you. Sure. Right? Because they wanted to, when you're in traffic, if somebody starts moving in front, you want to stop before, they get in front of you. So they challenged the neural network to predict if anybody was going to cut in front. And then if it was right or wrong, they would save those examples and they would use them to train it. And then there was a day I remember it was March 2018, because they turned on this feature and everybody started complaining, right? Because if you're driving in traffic, it's just like stopping for no reason all the time. Because if it thought there was going to be a cut-in, it would slow down, right? And once again, the people who wrote the initial code, they were very careful. Like, they don't want to have an accident. So just in case, they stop, right? But after they run it for a little while, they get more training data, they feed it in the system confidence goes up, and the people who write the code that use the output of the neural network, they also become more confident. Like, for instance, they say, if it's 0.9, stop. And then they watch that in the real world for a little while. And then after a while, they're like, no, 0.9 is too much. It should be 0.85 and we stop, or 0.95 and we stop. And so they learn a little bit too, and it gets refined. And so what happened is, over a period of 3 weeks, the car went from, it was fine, but it couldn't detect cut-ins. And then they turned on cut-ins, and all of a sudden it seemed terrible. And everybody was complaining about how terrible it was. And 3 weeks later, it was fine again. Because it took them, 3 more iterations to gather the data, refine what they were doing, push that out to the fleet. And then, a month after they introduced the cut-in thing, the car could accurately predict and stop if somebody was pulling in front of you, even if they didn't signal, or even if it was really close. And the net result of that was that people's experience of riding in the car in traffic became much smoother. Because previously, if somebody pulled in front of you, the car wouldn't stop until it was in front of you. Right? It wouldn't see it coming. It wasn't good at predicting that. So so sometimes you'd be riding in the car and somebody'd pull in front of you and you'd see them pulling over and you're like, why is the car stopping? Why isn't it stopping? And then they'd get in front of you and boom, the car would suddenly stop. And it was upsetting. People would complain about that. When the cut-in indicator started working, that just never happened anymore because it could accurately tell if somebody was going to pull in front of you, and it would respond the same way a human would. I mean, it's not superhuman. If somebody suddenly pulls in front of you, just like a human, it might not be able to anticipate it. But if somebody was slowly moving their way over, it would see it and it would open up a space and and then it got smoother. So the improvement of autopilot is hundreds and hundreds of features like that, little features. They get brought in. Initially, they don't work very well. They get refined and they work better. And then eventually, once you have a lot of those features, you can build other features on top of those features too. For instance, the car used to be very bad at when it wanted to leave a freeway. When you're on the freeway, it used to be very timid about getting off the freeway, and it knew it was bad. So it would do a thing where, like 2 miles before your exit, it would get in the right lane and it would just sit there, right? Because it doesn't want to miss the exit, right? Because people get mad. But now it's in the slow lane and there's cars merging in and out, and it seems, it just seems. So then, as it got better at being able to move over, they would wait longer to get into the lane and they would merge, but it would still want a pretty big space when it moved over. It wanted to have plenty of space behind it and plenty of space in front of it. As a human being, you can kind of do a thing where, you want to move over and the space is a little tight and you kind of move a little bit and the people around you.
When you're filtering out of the highway, right? And then you're wanting to move over the lane and people around you kind of, you're monitoring the people around you, right? So if they slow down, then it's okay for you to. I think that's where you.
Yeah, well, I was just the history of this feature was that it was terrible, and then it was kind of okay, and now it's much better than I am because one of the things the car has is it can see in all directions at the same time, and of course, one thing that's tricky in traffic is sometimes when you're trying to maneuver, you have to watch the car ahead of you and behind you at the same time, just in case.
Yeah.
And that means, you don't want to try to enter a small space between two cars because what if the guy in front of you stops? And what if the guy behind you isn't leaving enough space? But for the car, that's no problem because it can see them both at the same time, right?
Sure.
It knows it's not going to get upset. So these days I see the car, it makes lane changes that are just impossible for me and it's fine. So,
So